If you have not seen it, there's no point in,
When is it? It's due next week, right?
Next week. So you don't, when do you open it? Okay. So all the problems are on Rayleigh-Ritz method. When you apply Rayleigh-Ritz method, you have to make sure the function you assume satisfies the boundary conditions. For example, in the first problem, which is a simply supported beam, the beam is supported on both ends. I'm assuming a function c times x minus 1. The length is 1 meter. So you have to make sure it satisfies the boundary condition. This problem is the deflection should be 0 at the toe support. If you go to the next problem, the boundary condition is at the cantilevered support, cantilevered end, both deflection and the slope should be equal to 0. So the way the function is given, it doesn't satisfy. So you have to force it to adjust the constants to make it satisfies this equation. That is the first step. Once you start with an acceptable function, you calculate the strain energy using the simple formula EI over 2 integral 0 to L, second derivative of the deflection square dx. So that will be a function of some constant C1, C2, whatever constants in your problem, A, B, C, or C1, C2. Then we have to calculate the potential of external forces with a negative sign. In this case, there are two types of forces, a distributed force and a couple. For the distributed force, 0 to L, the distributed force itself is a function of x. So you have to figure out that function, okay? Px, Pyx. You have to figure out that function, then Vx dx. In this case, I can give you a clue. The Pyx, first it acts downward, so it should be a negative sign itself in the function. It's a linear function, so it should be. So when you put x equal to 0, the intensity is 0. When you put x equal to L, the intensity is P0. So this is the way the Py, the pressure, varies with a negative sign here. Then there is a couple there, okay? Couple do work with the rotation. So this couple is a positive couple. So the negative sign stays in the formula, negative c times. The amount of rotation is dv by dx at the evaluated at x equal to L. So by the end of the day, your V will be in terms of C1, C2, C3, C4, whatever left, okay? After you impose the boundary conditions. Then you evaluate pi in terms of constants, and then finally you differentiate the pi with respect to various constant you have in your problem to solve for the constant. Once you find the unknown constants, you have an approximate deflection shape. You can plot it nicely. And also if you want to find the bending moment, after you have to go back and use the same formula, EI d square V dx square, that is my bending moment, and then the shear force Vy is given by minus dm by dx. This is an easy formula to remember. Okay? So this is how you do apply Rayleigh-Ritz method. Okay. Definitely there will be, I don't know when is I think the exam is coming right after the spring break, I think, the Friday. So I think use the spring break wisely to prepare for the exam. If you want, I can post some sample problems for you to practice. Okay, today we start the proper beam finite element method. So what is the problem? So I have a beam. It is supported some way. It can be redundant support, doesn't matter. I can have a support here. That's the beauty of finite element method. You can have, it's called continuous beam. You can have a lot of supports if you want. You can solve using your mechanics of materials knowledge. That's fine. Then it is subjected to, so the coordinate system is x, y. It's subjected to a lot of forces, a distributed force, a concentrated force here and there, a couple here at this point, a concentrated force, a weight of something hanging, an engine or something from the wing, something. There's a lot of forces acting. So we have to solve by finite element method. So what we do is we take the beam and divide into number of elements. Okay, and when you divide into number of elements, so this is element 1, 2, 3, 4, 5. The elements always are connected in nodes. That's the finite element. Finite element, elements talk to each other only at the nodes. So this is node 1, node 2, node 3, node 4, node 5, node 6. Now you may ask how big or how long or how short an element should be. The answer will become clear when you understand how the element works. If I say something now, it should be very short, you'll be wasting your resources by making very short elements. That's not the idea. There is a reason why an element should be of certain length. You'll understand once you solve the problems. Okay. Now, in finite element, you are allowed to apply forces. Okay. So what are we solving for? Instead of solving for the deflections, in the beam theory, we solve for deflection, Vx. Now, in finite element, we don't do that. We solve for deflection and slope at the nodes. We call the deflection at this node V1. The slope, sometimes I call it rotation, both are same. I told you slope is, but they are different. This is slope, this is rotation. But in Euler-Bernoulli beam theory, both are same. Slope is the slope of the deflection curve. Rotation is the rotation of the cross section. We assumed a priori that they are same. Okay? So that is V1 theta 1, V2 theta 2. My V today looks like U, I don't know why. I think spring break is closer, I think. V4, V5 theta 5, V6 theta. So in finite element, we solve only, any problem there? Okay. The only thing we solve in finite element is nodal degrees of freedom. In a beam element, the nodal degrees of freedom are a displacement or deflection and the rotation. So there are two degrees of freedom. The two DOFs are deflection and rotation of the cross section. Deflection and rotation. So we solve only finite number of degrees of freedom instead of a continuous function. That's why the name finite element method. Okay. Now in finite element method, you are allowed to apply forces only at the nodes. You can't apply forces elsewhere. So at each node you are allowed to apply a force corresponding to the degrees of freedom. So at this node I can apply a force F1 and a couple C1. At this node I can apply a force F2, a couple C2, etc. F6, C6. Now you may ask, in my problem there is a force here, what I should do? What is the answer? Put a node there, don't ask me. Wherever you see a concentrated force, put a node there. Wherever you see a support, because support is a reaction, the support is going to apply a force. So put a node there. So now I'm answering how long or how short the element should be. There should be nodes at the supports. There should be nodes at points where forces and concentrated forces and couples are applied. Okay. The only question is, if you have a distributed force, what do you do? That is the next chapter, next section. I will talk about it. For now, assume there are only concentrated forces and concentrated couples. Okay. Now, what we want to solve? We want to solve for the deflection. I told you in finite element we solve only for this. That means what we are solving is, at the end of the day, at this point goes here, it has a slope this much. This point goes here, it has a slope this much. This point comes here, it has a slope this much. And that's all. In the boundary condition, that the deflection is fixed. Somebody tells you. So slope may not be, maybe unknown, whatever. So in finite element, we solve only nodal degrees of freedom. At every point, what the deflection V and what is the slope. Now the question is, what happens in between? So in between, we interpolate. So that is the key thing in finite element, interpolation. Now you see there, what I say is totally different from spring element and truss element. The reason is two. The spring and truss element, we use what called direct method, direct stiffness method. Here we are using the energy method. That is the key difference. The language is different. Second thing is the truss and springs were naturally discretized. You don't have to put a node anywhere. The nodes are already there, the elements are already there, given to you. Whereas in the beam, now it is your responsibility to put the nodes and elements. So that is the difference now on. From now on, we are going to be in this energy method. Do you have a question? Yeah.
Should you try and pick equally spaced elements?
The question is, should we try equally spaced elements? No.
So okay.
No, you don't. Yeah, that will be waste. Okay. You'll find out. Be patient. You'll understand. I won't even explicitly say how to do it at the end of my lectures, or you'll say, yeah, I got it. You don't have to answer. You won't even ask me the question. See, a good teacher is one who doesn't require students to come for office hours. None of you come to my office hours. So that's how I know I'm a good teacher. Makes sense? They come to your office hours? No? I think we are doing a good job. Same thing. But Ting Dong gets a lot of people for the day before the project. Okay. So that comes interpolation. So take a typical element. A typical element. I don't know whether we call node 1 and node 2 or node I and node j. I think we will stick to node 1, node 2. A typical element, node 1, node 2, and it has a length L and the flexural rigidity EI. My question is, I want to interpolate. So I know V1 theta 1 at this point. I know V2 theta 2 at this point. It makes convenient to introduce a coordinate system, what is called local coordinate system. These are all in the book. You should read the book, okay? Starting from here, we call it S equal to 0 here, and S equal to 1 here always. The reason is a natural coordinate system. By putting S equal to 1 there, whatever I do is common for all the elements. Now, the transformation between, suppose if you call this x, now x1, the coordinate of this x2, S is given by so that is the transformation between, if x is equal to x1, S is equal to 0, when x equal to x2, this will be equal to 1. So it's very simple. My question is, I want to interpolate the displacement v as a function of s. That's convenient. I want to use polynomials which are easy to integrate. There are a lot of formulas available in the computer. So my question to you is very quickly, I can't wait too long. What order polynomial? See, we saw sine function is ruled out. We saw some problem with the second order polynomial, third order polynomial, fourth order. The various polynomials are possible. What polynomial? What does it mean? Fourth order? Fourth order? Up to 4? X to the 4? That means you are saying C0 plus C1x plus C2x squared plus C3x cubed plus C4x to the 4? You don't want to change your mind? Do you want to change your mind? No. Why you chose 4, power 4? You said 4.
Yeah, I read it in the book.
I thought you knew it. Anyone. It's not the fourth order, okay? It's a polynomial with 4 constants. So in this case, a third order polynomial. The reason we want only 4 constants is we have nearly 4 pieces of information. I know the deflection and slope here. I know the deflection and slope here. The only way I can interpolate by having 4 equations. If I have like you said, 4th order polynomial, quartic, it's called quartic polynomial, there will be 5 constants, I don't have the information. If I have less than that, then I have superfluous information, it won't work. So how do we evaluate the constant? So this is exactly like Rayleigh-Ritz method. Rayleigh-Ritz method, you assume a polynomial, and then jump to calculate the strain energy, everything. Here we can't do it. We cannot use these arbitrary constants. We have to convert them into nodal degrees of freedom. How do we do that? I know V0 is going to be eventually V1. That means this constant C0 should be equal to V1. Okay? Similarly, V1 at the other end should be equal to V2. So I can set up an equation, C0 plus C1 plus C2 plus C3 should be equal to 1. Then I differentiate dV dx can be written as dV ds ds dx. Okay. What is ds dx? 1 over L. So this will be 1 over L dV. I think you have to remember this relation always. dV dx, which is the slope of the deflection curve, is given by 1 over L dV ds. I'm not happy with this. Is it correct? Yeah. Yeah, that's correct. Because our V is always going to be sometime as a function of S, so we should be able to go back and forth. So we can do the same thing. So dV dx at s equal to 0 is equal to theta 1. Okay. So how do we do that? So you differentiate this, and then put s equal to 0. You should get, when you go home, okay, you should be able to set up. I'm not going to do it. It is in the notes. It is in the PowerPoint also. Similarly, dV dx at s equal to 1 should be equal to theta 2. When you do all this, let me open that the PowerPoint, because the equations are long. Okay, so we are in the interpolation. So by the time we finish interpolation, what we do is we get Vs is equal to V1, a function called N1. I'll tell what N1 is, plus L theta 1, I believe, times N2 plus V2 in 3s plus L theta 2 in 4s. We get the 4 functions. So what we have done is we have interpolated the deflection in between in terms of V1 theta 1, V2 theta 2, and then there are 4 functions. These are called interpolation functions or shape functions. Interpolation functions. Or shape functions. The reason is, you know what interpolation function is? That's obvious. Shape function, because it tells you the shape of the deformed structure, in this case deformed beam. Now, how does this function look like? It is in the box there. You can see that function. How do we did that? After we solve for this constant in terms of V1, V2, etc., I made a mistake. Nobody corrected me. We always interpolate in terms of S, because we already, okay. So finally the functions are given here. These are called shape functions. Now, if you look at if you want to plot these functions, they have some beautiful shape. Okay, that's very important. N1, the first function, the first function. So I'm going to plot all these functions go from 0 to 1, s, okay? And then if you plot the first function, it's a function will value take 1 at this end. Put the first function, put s equal to 0, you will see 1. And if you put s equal to 1, it will become 0. You can see that. And also the slope will be 0, slope here will be 0. So this function will be is a cubic function, look like a snail. Okay. So out of the 4 degrees of freedom, only one will light up at this point. All other degrees of freedom will be 0 at the two ends. Yeah, you have a question? Okay, if you look at the first shape function, this is the shape. It will be 1 at this node. It will be 0 at the other node. And also if you look at the slope, other degrees of freedom, it will be 0 here and there. Out of the 4 degrees of freedom, the 2 deflection and 2 slopes, only one will light up. All other 3 will be 0 for the first shape function. Okay. The second shape function is opposite. It will be 0 here. It will have a unit slope here. It will have a unit slope, and again everything will be 0 here. Deflection also is 0 here. So it will be like this. The third function, the reason is because of this. See, when you put s equal to 0, all these guys go to sleep. You should get v0 should be equal to v1. When you put s equal to 1, all these people should go to sleep. There should be no L. Nobody corrected me. The L, yeah, L will be there.
No, I don't think he needs L. Yeah. N4 and N2, those shape functions already have L in it. So if you left the L there, you'd be multiplying by L squared.
I'm fine. Yeah. This is fine. L, this is good. So V2, N3. N3 will be, so this is N2. N3 will be like the opposite of, it will be 0, 0 here, and then it will be 1 here. This is N3. This is N2. N4. Okay, can anybody draw N4? N4, it should have positive slope here, slope equal to 1, and all other degrees of freedom will be 0. So it has to be below. So it will come like this. So you can see N4. So these are the 4 shapes. It's called Hermite polynomials. Hermite, it is given there. So these shape functions. So we derive such shape functions for every element. Once you derive the shape functions, half the job is done. If you're doing a PhD, nowadays nobody does PhD in developing a new element, all done almost. So we all use Abacus, Nastran, we all use commercial programs. When I was like you, we had to write our own element. That means we have to come up with the shape functions, interpolation functions. It's a lot of fun. We had a lot of fun. So we are successfully.
For your race, where it says v1 equals v2, right, where you just race, should that be c0 plus c1 plus c2 plus c3 equals 1 or v2?
Yeah, you get the point. You don't? V1 should be equal to V1, yeah. It should be equal to 1, V1, yeah. So what we accomplish is this happens in each element. So you have several elements, each will have different length, doesn't matter, okay? So this is node 1. So we have V1 theta 1. We are going to solve V2 theta 2, V3 theta 3. At the end of the day, you solve for, in the finite element, you solve for all these degrees of freedom. So when you find the deflection at this point, you plot the curve like that. Now, one of the things in finite element is by the time you solve, when you plot the deflection of the beam, they should not have a broken beam. If the deflection is if the deflection of this beam element is like this, if the deflection is like that, if the deflection is like that, it's a broken element. You cannot have broken elements. The element deflection has to be continuous. The slope has to be continuous. Even if the slope is not continuous, it's a broken element. So at every node, the deflection and slope has to be continuous. But that is already assured, because at this node, at this point, whether you look at this element 1 or element 2, the deflection and slope are given by this value. What is V2 theta 2? The deflection and the slope at this node, whether it belongs to element 1 or when you go to element 2, use the same value V2 theta 2 here. That is the beauty of finite element method. Different from Rayleigh-Ritz method is, that's why Rayleigh-Ritz method is one continuous function, the entire structure. The finite element is very clever. It breaks the function into number of pieces, small pieces, and approximate by simple polynomial. That is one thing. Second thing is, it assures you after you solve the problem, there won't be any broken elements. At this junction, of course, these are all continuous, we know that. It's a third order cubic polynomial. At this point, there is always a unique displacement and unique slope at each node that ensures a continuity of deflection here, here, here. A priori, even before you solve the problem, by choosing the interpolation polynomial such that you ensure compatible deflection. These are all nuances of finite element method. Some people explain, some people don't explain. So now what we have done is we have chosen the function. If you have done a Rayleigh-Ritz method already, somebody has done it, so you know. Rayleigh-Ritz method, I give you the function, but here the function is already given. I told you have to satisfy the boundary condition. The boundary condition is already satisfied, because if you use a cantilever beam, we know at this point V equal to 0, theta equal to 0. The polynomial, we input that. So the boundary condition is also automatically satisfied in finite element method. So we have a very admissible deflection shape. Now we have to choose the correct one using the minimum potential energy principle. So what we are going to do, the first step is to calculate the strain energy in the beam. This is the strain energy in the beam. Now energy is a scalar quantity, so that can be thought of strain energy in all the, I don't know, E equal to 1 to number of elements, UE. Here NE is this is the beauty of energy methods. I can add energies. See, vectors and tensors very difficult to add, whereas energy is a scalar quantity. I calculate energy in each element and then add them. That is the total energy in the beam. So now we can focus on how to calculate energy in one typical element that has a length L, it has a flexural rigidity I, and it has a deflection given by the polynomial. Now UE is given by x1 to x2. EI, I'm going to take, another thing I forgot to tell you. In finite element, each element must have a constant EI. You cannot have variable EI. If you have variable EI shaft, what do you do? Suppose I have a shaft that is tapered like this. Which EI use? You have to use constant EI. I told you how to break into number of elements. So you break into number of elements. Now I tell you, you can use only one EI, then you use some kind of average EI. So you make it a stepped bar. So in finite element, you can solve only a stepped bar. You cannot solve a tapered bar. Now that tells you how short or how long the element should be, isn't it? Because if you try to model the whole tapered shaft as one element, you are making gross approximation, because you'll be using some average diameter, which is not good. That's why if you break into a number of elements, then you say, I'm going to make it a uniform diameter shaft. It's just a reasonable approximation. And also you'd be asked to do a convergence study. Usually you asked to show your boss what is the answer with 10 elements, what is the answer with 15 elements, what is the answer with 20 elements. Then the boss will say you can stop now. Okay, I see that your results are converging. Okay, so convergence is the last chapter if you read the syllabus. Okay, now how do you find? So EI is d square v dx square. This is the formula. Nobody can change the formula. X1 is the whatever coordinate of this node. X2 is whatever coordinate of this node. Now we want to convert this into S coordinate because that's integration substitution of change of variables. We did that already. We have this equation S equal to x minus x1 over L. dv dx is 1 over L dv ds, and d square v dx square is 1 over L square d square v ds square. Sorry, you can see. You don't have to see, look like, yeah, it is in the book. Yeah. So it is 1 over L square d square v ds square. So we can substitute in this UE equal to EI. Okay. So this is square, so it will be EI over L to the 4. L to the 4, remember that. The limit will become 0 to 1. Here you can write d square v ds square whole thing squared. And then here dx is L ds. Do you see that? Dx is L ds. L ds. So if you put L, so 1 L will cancel, 1 L will cancel. So you get a nice equation, EI over 2. I forgot 1/2. Nobody in this class corrects me. There should be 1/2 in the strain energy always. 1/2 EI. Spring energy is 1/2 kx square. So there should be a 1/2 here. 1/2 EI over L cube integral 0 to 1 d square v ds square whole thing square ds. This is a very important expression. So now we are going to substitute. So I told you a minute ago, Vs, I don't want to, yeah, plenty of time. Vs can be written as this is a 1/4 matrix, this is a 4/1 matrix, and this is just a deflection. Okay. So instead of writing as a polynomial, I kind of separate the functions. These are all functions of S. Okay. Everything is a function of S. I write as a matrix form, row matrix, and I write this degrees of freedom as a column. You think I'm making unnecessarily complicated, but you will see the beauty of it. So if you find a second derivative, d square v ds square, I can write the v double primed for convenience. I don't have to differentiate this degrees of freedom. They are kind of constants. We don't know what they are now, but they are constants. So it can be written as n1 double prime, L is a constant, n2 double prime, n3 double prime, L n4 double prime times, I'm going to write a shorthand form. We can call them QE, meaning that these are the degrees of freedom of the element E. Okay, these are DOFs of element E. Just element E. Just call it Q. That way, sometimes I just call it Q. I don't even put the E because we are talking about one element. Okay. Now, I'm going to write this also as V1 theta 1, V2 theta 2 times N1, Ln2, N3, Ln4. You may wonder why I do this. This is also correct. Here what I have done is I have written the degrees of freedom as a row matrix and shape functions as a column n double prime. Both are acceptable form. You may wonder why I do that. We will see in a minute. Now I go back to the strain energy of the element. The strain energy of the element is always 1/2 EI over L cubed integral 0 to 1. What do I have? D square V dx square ds square squared. There are two terms I have to multiply. For the two terms, what I'm going to do is, for the first term, I'm going to use this form. I'm going to write this as Q transpose and N double prime. What it means is I'm writing this form. I write the degrees of freedom in a row form, and this, sorry, I forgot, nobody corrects me. This as a column form, second derivatives, okay? That is, for the second term, for the product, I'm going to use this nice form. So I'm going to write this N double prime as a row form, and then the degrees of freedom as a column form. Can you see here? And ds. Now you have to always check the matrix order. This is a 1/4 matrix. This is a 4/4. This is 4/1. This is 1/4. Sorry, I'm making a lot of mistakes today. This is 4/1. This is 4/1. This is 1/4. This is 4/1. See the beauty of it. If you multiply everything, you get 1/1, because energy is a scalar, it's not a matrix. Okay. Now another thing we note is these degrees of freedom are constants. They can come out of the integral sign. They don't have to stay inside the integral sign. Whereas this n prime, double prime matrices, the second derivative of the shape functions, cannot come out of the integral sign because they are functions of s. So I'm going to take the q's out of the integral sign, but when they come out of the integral sign, they cannot just go wherever they want. They have to take the proper exit. This q can't go only this side of the integral. This q can only come this side of the integral to maintain the order of multiplication of the matrix. So this will be 1/2. I'm going to put the q transpose here. The EA over L cube, I'm going to keep it as some kind of factor, EA over L cube, integral 0 to 1. Here I have all these shape functions, derivatives written in a column form. Then I have all the derivatives written in a row form. I'm going to integrate them and keep this degrees of freedom outside. Now this is 0 to 1. Now you can integrate this function very easily. The idea is for all the elements, sorry about that. So you can come here, there's a lot of room here. For all the elements, the beauty of this is for all the elements, the shape function is the same because they are in terms of natural coordinates s. So I have this second derivative somewhere in the book. I can integrate. When I integrate, I will get a matrix. This EA over L cube is going to tag along with the integration, and then I get a matrix called element stiffness matrix like this. This is the 4 degrees of freedom of the element written in a row form. This will be a 4/4. That's called element stiffness matrix. This is again degrees of freedom. Of course, UE is a 1/1 scalar number, where KE is called the element stiffness matrix of the beam element. So if you want to calculate in the exam, I will ask to calculate what is K23. something like that. But in general, the formula for Kij will be EI over L cubed of the element, integral 0 to 1. Can anybody tell from looking at it is a ith row and the jth column. If you know the matrix multiplication, you have to take the ith row on this matrix and jth column in this matrix and multiply. That's how you do the multiplication. So it will be Ni double prime Nj double prime ds, where I and j can vary from 1 to 4. So if I ask for K23, you just take EI over L cube, go to the third function, find that second function double derivative, second derivative, N3 second derivative ds. Suppose I ask for K32 also in the same problem, you don't waste your time because K32 is same as K23. You are going to switch this. How does it matter? So we realize Kij equal to Kji. So stiffness matrices are always symmetric matrices. All stiffness matrices are symmetric matrices. And also, if you take the diagonal element Kii, that is the diagonal element which will be given by Ei over L cube, integral 0 to 1, Ni double prime square ds. This will be always greater than 0. So this is a positive, for a positive semi-definite matrix, the diagonal elements of will be always greater than 0. They can never be 0. So you will find, you can tell from this, you're squaring a function and then integrating from 0 to 1, it will be always a positive number. Diagonal will be always greater than 0. Now how this K looks like, ta-da, we'll show you. Oh, it's not there. Oh, he didn't show it. Man. It is in the book. I wish they should. I think it's coming, yeah. It's coming, yeah. This is the celebrated element stiffness matrix, EI over L cubed. Then you can see a bunch of numbers. The length is inside, okay? So for each element, the stiffness matrix has to be different because each element has a different stiffness. Now, so now if you found there's suddenly a new explanation, new meaning for element stiffness matrix. Take it from me, for all the elements in finite element method, the strain energy of the element, in solid mechanics, strain energy of the element is always given by 1/2 Q transpose KQ. If you go back to the uniaxial bar, what is the, I need to tell this, I'm wasting time. If you take a uniaxial bar, what is the energy of a uniaxial bar element? 1/2, okay, or take a spring. Let's take a spring first. That will be easier. 1/2 K delta L square, okay? That is same as 1/2 K U2 minus U1 square, because the elongation is U2 minus U1 square. Now when you go home, verify this is same as 1/2 U1 U2 K minus K minus KK U1 U2. If you multiply these matrices, you will get this. It will be same as 1/2. K is common. K is common factor. K is a common factor. So you have, if you multiply these three matrices, the quadratic form is U1 square minus 2 U1 U2 plus U2 square, which is same as this one. So energy of an element in solid mechanics, any finite element, plate element, shell element, 3D solid elements, or whatever element is, always energy of the element is 1/2 Q transpose times the stiffness matrix of the element times Q. Never forget that. There is also another interpretation. How many of you have heard of Castigliano's theorem? Don't tell me, don't let me down. Somebody is nodding their head. Which course did you learn? Design. Really? That's amazing. Mechanical design?
Yeah.
I think you have good memory. What's your name? Luke? What last name? Okay. There's a guy who scored perfect score in the first exam or something. I forgot his name. Did you have a perfect score in the first exam? Did you have a perfect score in the first exam? No. I want to see that. It is not Nabil. Nabil Iqbal lost by a point. If you apply Castigliano's theorems, see, if you take an element, any typical element, E, if you draw a free body diagram, if you cut it and take it out of the finite element, the whole structure, Dr. Jenkins told you a long time ago, you have the free body diagram, you have to show all the forces acting on the element. In this element, let's say this is node 1, node 2, the forces acting are F1 and a couple are descent C1. This force F2, shear force F2, and the bending moment C2. So these are the 4 forces acting on an element. If you cut it, if you can see, the 4 forces correspond to the degrees of freedom V2, theta 2. We never talked about this little f1, little c1, little f2, c2 in the so far. If we derive the finite element stiffness matrix, that is the beauty of energy method. The energy method, you bypass these little guys. You don't even look at them. You directly go to the energy in the system and derive the stiffness matrix. But for your information, these forces, if you want to see F1, C1, F2, C2, the 4 forces acting on the beam element, they are also related by the stiffness matrix times V1. So there are 2 interpretations for the element stiffness matrix. One is this interpretation. Energy method claims the stiffness matrix meaning is 1/2 Q transpose KQ is the energy. What is the energy in the spring? 1/2 KX square, that 1/2 K delta L square. In the same form, you can write this as 1/2 delta L K delta L. 1/2 delta L K delta L. Same idea, 1/2 Q transpose KQ. That is one interpretation. The second interpretation is, if you take the element stiffness matrix, multiply this is a 4x4 matrix, this is a 4x1 degrees of freedom. If you take the element stiffness matrix and multiply the degrees of freedom of the element, you get the corresponding forces acting on the free body diagram of the element. This directly comes from the energy. What is the connection between this and this equation? Castigliano's theorem. Castigliano's theorem tells, if you know the energy of the system and if you differentiate with respect to displacements, you get the corresponding force. So this is also an acceptable definition of the spring stiffness matrix. Okay. So we have to stop here. Next class, I won't be here. Ting will continue this discussion. But rest assured, she's a good teacher. Okay.